this video, we will continue to explore chem activity number 7. We will be looking at teaching model number 6, parts 2 through to part 5. In these parts, we'll be introducing the various functional groups and where we'd expect to see their signals in an infrared spectrum. But also, we'll be looking at the various factors that affect where the signal will show up exactly. We've already mentioned that a typical carbon-hydrogen bond, where the carbon is sp3 hybridized, will show up in an infrared spectrum around 2900 centimeters to the minus 1. As it turns out, if the carbon is sp2 hybridized, or sp hybridized, then the signal shows up in a different spot. So carbon bonded to a hydrogen where the carbon is sp2 hybridized shows up around 3100 centimeters to the minus 1. Carbon that's sp hybridized bonded to a hydrogen shows up around 3300 centimeters to the minus 1. You can see that with hybridization changing from sp3 to sp, the wave number increases. Let's try to explain why that might be the case. And essentially, we're looking at the effect of hybridization on the signal. So you may recall that an sp3 hybrid orbital is the result of combining one s orbital with three p orbitals. As a result, 4 sp3 hybrid orbitals are generated. Each sp3 hybrid orbital would have more p character in that orbital compared to an sp hybrid orbital. This is because 3 p orbitals were used in combining to form that hybrid orbital. If we look at an sp2 hybrid orbital, recall that 1 s and 2 p's, and an sp, recall that that was the result of combining 1 s and 1 p. Also recall that electrons that are in a p orbital are found further from the nucleus than electrons found in an s orbital. Going from left to right, we'd say that there's an increase in s character of these orbitals. With an increase in s character, the electrons are found closer to the nucleus. We might expect that the electrons are held more tightly by the nucleus. Therefore, we might expect that a carbon-hydrogen bond is in fact a stronger bond. So the idea here is that with an increase in s character, there would be an increase in our force constant, which of course means an increase in the bond strength, which, as we saw before, corresponds to an increase in the frequency or the wave number that's required for the absorption. So it would make sense that a carbon-hydrogen bond where carbon is sp hybridized would absorb at a higher frequency or a higher wave number. This is actually very helpful in interpreting a spectra and trying to figure out whether or not there's a carbon making a bond to a hydrogen where the carbon is actually either involved in a double bond or carbon's involved in a triple bond. As an example, let's look at these spectra. So we're only looking at a small portion of the spectra, around 3000 centimeters to the minus 1. So for a typical alkane, so for instance, this spectra could correspond to a pentane, for instance, where these peaks here correspond to the carbon-hydrogen bond where the carbon is sp3 hybridized. So once again, remember that these peaks don't correspond to an sp3 hybridized carbon. They correspond to the carbon-hydrogen bond stretch where the carbon is sp3 hybridized. In this next example, we have, for instance, an alkene. So perhaps we have a propene. So in having a propene, it would mean that there are hydrogens, for instance, that are bonded to carbon where carbon is sp2 hybridized. So just to be clear here, and I'm just going to change my pen color to make this a little more apparent. This carbon here is sp2 hybridized, and it's making a bond to a hydrogen, and therefore the signal that we would expect to see would be above 3000. And so this, of course, corresponds to a carbon-hydrogen stretch where the carbon is sp2 hybridized. That's a very telltale peak that you would see in a spectrum if you anticipated that you had this alkene of this sort. Notice, however, that we also have, and I'll just change to, let's say, a green color, that we also have a hydrogen here, which is on a carbon that's sp3 hybridized. So that carbon there is sp3 hybridized, and correspondingly, we have a carbon-hydrogen stretch signal corresponding to a carbon that is sp3 hybridized. As you might expect, and I've mentioned this before, this signal is not actually that telling because a lot of molecules have a carbon-hydrogen stretch where the carbon is sp3 hybridized. Actually, what's more telling is when this peak is missing, because it's rather rare to have a structure, a molecule, where there are no sp3 hybridized carbons bonded to a hydrogen. Finally, an example of an alkene. So I'm just going to go back to my red color here. And a typical alkene could be this propyne. And in this particular case, we have a hydrogen at the end here. And this hydrogen is making a bond to a carbon that would be sp hybridized. So this carbon here is sp hybridized, and therefore it gives rise to this peak, which is around 3,300 centimeters to the -1. So that would be a carbon-hydrogen where the carbon is sp hybridized. Note that it's a very distinct peak, and so that's a unique situation, and if you see that peak, it's confirming that you've got this kind of moiety in your structure. But also notice once again that we do have this carbon that's sp3 hybridized making a bond to a hydrogen, sp3, and so that corresponds to this signal right here. So that was the effect of hybridization. I think it might be helpful now. Leave the slides for a minute and let's take a look at a chart that you have available. I'm looking at the chem activity number 7, and this is a chart that is found within this activity in teaching model number 7. Note that you will have available to you this chart during assignments and tests. You do not need to memorize these numbers, but it's a really good idea to get yourself familiar with the various types of functional groups and where you'd expect to find them in an infrared spectrum. We already saw in an earlier example the signal for an oxygen-hydrogen bond corresponding to 3,200 to 3,600. It's a very broad peak that's very characteristic. We'll come back to that also a little bit later. What we've just been talking about is the carbon-hydrogen bond, carbon-hydrogen bond, and carbon-hydrogen bond for sp hybridized, sp2 hybridized, and sp3 hybridized. Note that I don't actually label the hybridization on these carbons. That's something that you might want to do because it'll just remind you what's going on for those various signals. What we're going to do in the next example is look at a situation where we have, for instance, a ketone. Now notice all of these carbonyl groups, which of course ketone has. These signals are all occurring around 1700 to 1800. So that's a very common region to find the signal that corresponds to the C double bond oxygen stretch. Also relevant in this discussion will be the carbon double bond carbon stretch, which occurs somewhere between 1640 and 1680. Again, these are found on this chart, but it's helpful to anticipate that this is where you're going to find these sorts of signals and what sorts of factors can influence the signals. It is also worth pointing out that here are those triple bond signals that we already anticipated will be above the 2000s, and then some useful signals that are found in the fingerprint region. Again, often we don't try to interpret every signal that's in the fingerprint region, but sometimes it will be helpful to try to pick them out. This is especially true for some carbon-oxygen bonds. This can be helpful. It's helpful to look for this CH3 group, And then it's also helpful to look for these different patterns of carbon-hydrogen bonds where the carbon is part of an alkene. There are various patterns here about the alkene, and they show up in various spots in this fingerprint region.